Here. Our next talk is going to be from Glenn Letter from the University of Nebraska-Lincoln, and the title is Mathematical Modeling for Epidemiology and Ecology. So I will give the floor to Glenn. Thank you so much for being here.
So I'm going to talk about mathematical modeling for epidemiology and ecology, which is the title of a book that will be out soon. So it's a reworking of my first Mathematics for the Life Sciences book. It should be out in April. It was written for two purposes. One was to be a textbook for a possible undergraduate course in either mathematical modeling or mathematical biology, but also to be a source of problems and methods to supplement differential equations in modeling courses, which is the role that I'm talking about now. So in the talk, I'll identify some important special features of the book that you probably won't find anywhere else. I'll briefly show an overview of the contents, and then I'll spend the rest of the talk highlighting some of the topics, again, picking topics that you aren't likely to see anywhere else. Okay, so I'm putting a focus on mathematical modeling, and Tracy's talk was a great setup for me because she illustrated what mathematical modeling really is. It's not word problems. It's not applications of mathematics. It's designing mathematical models, analyzing the mathematical models by thinking about the effect of parameters on the behavior of the system, and then analyzing and then looking back at the real world to see whether your model results made sense. So in the book, many model derivations appear in the text and the problem. I discuss alternative choices for biological assumptions. A lot of problems contain symbolic parameters, as in Tracy's modeling. Many problems ask for a biological interpretation of results, and there are numerous projects that also require modeling. I also have an emphasis on scientific computation. The book can be used without doing scientific computation, but you're missing about a third of modeling if you don't. Modeling requires simulation as well as analysis. In my view, students need to learn to use the programming environment themselves. And so I've tried to make that as easy for students as possible. The book comes with 22 MATLAB programs. No prior programming experience is needed. I've used these programs with students before, and it is true that no prior programming experience is needed. There's an appendix that has a minimal MATLAB tutorial that does a line-by-line explanations of the two simplest programs. The programs are structured to make them easy to modify for new experiments or to alter for different models, because all the model-specific and scenario-specific code is in a small section at the beginning of each program. In one of the topics I talk about later in this talk, I'll show you a snippet of my simplest program. This is the general table of contents. In my presentation of table of contents, I've grayed out topics that are not relevant for differential equations, and I've highlighted in blue topics that I will say at least a little bit more about in the talk. So I won't be talking about discrete linear systems. The main point there for differential equations is just to introduce eigenvalues for students who haven't had a linear algebra course. Chapter 3 on mechanistic modeling is the longest chapter in the book, and you can think of it as divided up into sub-portions. The first two sections are just about specific processes that are incorporated into models, transition processes like disease recovery, and interaction processes like disease transmission. And I'll be talking about two of the transition processes later, my vaccination model and multi-phase transition processes. Then there is a section on compartment analysis, which uses the SEIR epidemic model to illustrate the method, and a section that does model analysis, but it doesn't do dynamical system analysis. That's something you do for an endemic model. Instead, it looks at things like how many people are still susceptible when the epidemic ends. Then there's a case study that includes two COVID-19 scenarios, which I've used in teaching materials. I consider section 3.6 to be one of the most important in the book because this is where you learn scaling. And then the chapter ends with 3 case studies. The last one, adding demographics to a disease model, is again something I will talk about later in this talk. Chapter 4 is on single populations, and I will just talk about one topic from here. And chapter 6, there are a couple of topics here that will be in my talk tomorrow, so I'm not going to spend time on them now. So let's start with vaccination. And so here's an SIR model that includes vaccination, and I've grayed out everything that isn't about vaccination. So the part that isn't grayed out, we can write down as an isolated single cohort vaccination model. And in the standard formulation of vaccination, it's just the same as radioactive decay. S of 0 is equal to 1 because the population is measured in cohorts. So what's wrong with this implementation of vaccination? So if I had time, I'd ask for suggestions from the audience, but instead I'll tell you the 3 things that are wrong with it. It's applied to the entire susceptible class, when in reality, there are people who are unable to take the vaccine and many people who are unwilling. It assumes an unlimited supply, when in reality, at the beginning of a vaccination campaign, there's hardly any supply at all. And it assumes instantaneous distribution, when in reality, distribution has to be accomplished by a limited number of healthcare workers. So all 3 of these things are flaws in the isolated, using the radioactive decay model. So let's correct them one at a time. Limited acceptance is pretty easy. Let's assume a fraction A of the population is willing and able to be vaccinated. And let's let W be the population fraction that is waiting for vaccination. This is not part of the epidemiology model, though it interacts with it, because when vaccination is scheduled, there is no effort made to limit vaccination to people who are still susceptible. People who are recovered can get vaccinated too. So W is not a subset of S, it's a different category altogether. It's a non-epidemiological category. Next, let's look at limited supply. This is fairly easy to deal with as well. Instead of a rate constant fee, let's put in a rate function that has a maximum of fee. So this rate function starts out at 0. It increases over time until some time tau at which it achieves the maximum value of fee. The simplest such model assumes that G is piecewise linear. When I wrote this down in the first time, I thought this is too simple, but you'll see it works great. And the last thing, which is a little more challenging, is limited distribution capacity. And the idea here was that, and here's where modeling really comes in. Tracy will appreciate this particularly. The idea is that vaccinators are like enzyme molecules in enzyme kinetics. And the people who get vaccinated are like the substrate. And so a Michaelis-Menten kind of model should work. And so if you take P equal to 1 in this formula, that's the Michaelis-Menten model with the extra factor G of T. So the idea is that there's a bound to how large the vaccination rate can be. If there's a huge number of people, you can still only vaccinate people at the speed that is possible based on healthcare capacity. P equal 2 corresponds to the ecological model of Holling type 3, which is actually the one I'm going to use. So these limits are only needed for scenarios with a new vaccine. Okay, so how does it fit to data? Well, the plot in B is the black is the model, and the red, which you really can't see, is the CDC data. So it fits the data really, really well. I don't have time to talk about the plot on the left, so I'll just leave that. Here is a program that students can use to reproduce this graph. So my program doesn't actually produce that graph. What this program does is it takes the simplest vaccination function and uses 2 different values of A. So in order for students to change this, they need to get rid of one of the values of A. They need to add lines for K and tau, the additional parameters, and they need to replace this right-hand side here with the appropriate function. That's not a lot of work for students to have to do. The rest of the program, where the extra coding is, doesn't change. And this essentially is a cut down version of a general program that's in the group of 22 that does just any ODE simulations, any systems of ODEs. Okay, next let's talk about transitions. So a single phase transition is like radioactive decay. If the mean time is 1 over mu, then the rate constant is mu. A two-phase transition would have the same mean time, but now it has two different phases. So you might be in the first phase waiting to join the second, or you might be in the second phase waiting to be finished. And so the rate constant for each phase is 2 times mu because you're only spending half the time in each of the two phases. Phase 1 is just like the single phase transition. Phase 2 starts out with an initial population of 0 because everybody starts in phase 1. And Y2 is populated by people who are leaving phase 1, and then people leave phase 2 in the usual way. And so you can solve that system of differential equations and get this answer. And you could have any value for K. You could write down the general formula for a K phase transition. And here's what the results look like. This is the remaining fraction infected from an initial cohort. The dark blue one is the single phase transition, and it's not very good for disease recovery. This would say that more people in this cohort recover on day 1 than on day 8, even though the mean, well, say day 5. The mean recovery time is 5 days, but more people recover on day 1 than day 5. That's clearly wrong. The purple curve for K equals 6 is much more realistic. Not that many people recover right at the beginning, and not that many people recover late. Most people recover in the middle. It's okay to use this for teaching, but you should consider a multi-phase transition for some research problems. And whether you actually need to do that is an issue explored in one of the projects in the book. Okay, next let's talk about adding demographics to a disease model. So this is a simple SIR model in which I have natural death in each category, and I have the possibility of disease-induced death if alpha is greater than 0, and I want to add a birth rate to make a sensible model. So what do I do? Well, the usual choice is a constant rate, usually capital lambda is the symbol used for that. I like to choose mu for the constant rate, as I showed earlier, so that the baseline population is 1. Then you don't need to scale the populations. It's silly to use a different value and then have to scale the populations. You might think that if you want a density-dependent birth rate, you should just make it proportional to the population, but this doesn't actually do anything because it exactly compensates for natural deaths. So if alpha is greater than 0, the birth rate is too small to replace the people who die from the disease and the population crashes eventually. If alpha is 0, then you didn't need the factor of n, which is always equal to 1. So under no circumstances is mu n a good choice. But if you want density dependence, you could try a birth rate based on logistic growth. So here's the logistic growth equation applied to the total population, which now is not going to be constant. The total death rate is still mu n. So growth is birth minus death. So if I know the growth that I want and I know the death that I want, well, then green is just blue plus red. So I get a birth rate function that has two components. It has the component that replaces the people who die naturally, plus a component that tries to adjust for people dying of the disease by pushing the population towards a carrying capacity. This is a better mechanistic model, but as in other model modifications, it turns out it only makes a noticeable difference if the death rate is high. So under most circumstances, we're justified in using the constant birth rate model that most people use. Here, though, we've actually studied the question in using mathematical modeling and come up with the conclusion, not on the basis of mathematical convenience, but on the basis of good modeling. Okay, lastly, I want to spend a fair amount of time talking about using structures to do phase line analysis. So many differential equations courses now include phase line analysis for single differential equations. Here's a single differential equation. It has logistic growth and it has Holling type 3 consumption, so it's similar to the vaccination model. C represents the number of consumers. So this is essentially the prey equation from a predator-prey model, but I'm thinking of C as being a constant rather than a variable. That turns the two-dimensional predator-prey model into a one-dimensional model. So the usual way to study this with a phase line is to plot the whole function f of x and see where f changes sign. That's not so good here because this f is a complicated function with two parameters. So we'll need to select specific pairs, p and c. And worse yet, it's hard to do any modeling because we'll have to start over if we change either of the two parameters. We'd like to see what effect one of the parameters has on the model, but if I have to start over when I change either of the parameters, then that's a lot of extra work. It's not the only option. We could think of this function f as being an increase part minus a decrease part, and we could draw a blue graph for the increase and a red graph for the decrease, and then the equilibria are where they cross, and whichever one is bigger determines whether we're increasing or decreasing. So this is every bit as good as following f. It's just as easy to tell whether blue is bigger than red than it is to tell whether f is positive. And in fact, it's more intuitive. But we can do even better than that by removing a common non-negative factor to make the functions easier. So for example, here, if I remove the factor x that's common to both terms, then I've changed the first term from quadratic to linear. That makes it simpler. So in principle, it seems like removing a common non-negative factor might help us. Then what's left is not actually the increase function, but it's a factor of the increase function, and it represents the increase function, which is why I have it in quotation marks. So structurally, symbolically, f of x is now being factored into a w of x times g of x minus h of x, and I want to choose w so that it's 0 when x is 0 and positive else otherwise. And the reason I'm doing that is that now I don't need to think much about w. Equilibria will have g equal h, or they'll have w equals 0, but w equals 0 simply means x equals 0. So I just have to make sure I remember that x equals 0 is an equilibrium, even though g is not equal to h there. And to determine whether x is increasing or not, I don't need to worry about w because it's never negative. So let's look at two possible implementations of this idea, because factoring here is not unique. So I mentioned that you could factor this by removing a factor of x. That's the obvious way to do it, but it still has the problem that if I want to graph the red curve, I still need to do a different graph every time I change either c or p. Instead, though, I could factor out the extra factor p plus x squared that's in the denominator. This is by no means obvious, but once you see it, then it's clear why it's going to be beneficial. Because now the blue curve is nonlinear and the red curve is linear, but the red curve has a parameter in it. So if I want to fix p and choose a family of c values, I only need one graph for the whole family. I don't need to change the graph just because I've changed c. And so here's how it plays out in practice. This is my last actual slide. So in these graphs, the blue curve is the fixed increase function when p is 0.01, and the red curves in the first graph are for different values of c. So you can see there's some bifurcation going on here. There are c values that have only one intersection for a large x. There are c values that have only one for a small x, and then there are c values that have 3. Let's look in more detail at one of those. So for that one, the equilibria are where the blue and red curves cross, and also at the origin. For each of the regions between equilibria, you just look to see which is bigger, blue or red. If blue is bigger, then the arrow goes to the right. If red is bigger, then the arrow goes to the left. And just like any other phase line analysis, the arrows tell you which of the equilibria are stable and which are unstable. So in this system, we have two stable equilibria. We have a very important bifurcation point here, in which if you start above it, you'll go to the higher equilibrium, and if you start below it, you'll go to the lower. And so finally, I want to end with a little bit of shameless self-promotion, which I apologize for. So this material was from my book, which is going to be out by April. And another feature of the book that I didn't mention in this talk is linked problem sets. And so I'm going to talk about linked problem sets and present two of these in detail in my talk tomorrow. Find me during the expo or shoot me an email if you want to chat, or as I said, shoot me an email. Thank you. So I'll take questions.
Hey, Glenn, I found your pandemic modeling, your epidemiology modeling interesting. I actually used to work for IBM recently, and I used an SEIR model to predict COVID case counts for different countries as well as the state of Hawaii for the Joint Artificial Intelligence Center and Indo-PACOM and things like that. And I think the biggest challenge for us was having an accurate forecast beyond 2 to 3 weeks because we didn't know how the reproduction number was going to change, because it changed a lot based on lockdowns and things like that.
So that's something that I didn't have time to talk about, but in my section 3.5, I have 2 scenarios from the COVID pandemic. And the first of those scenarios I created in March 2020 when the COVID pandemic was really fresh, and then just modified it a little later when we knew more. It's a modification of the SEIR model in which the infectious class is broken into 3 groups: asymptomatic, regular infectious, and pre-hospitalized. And the reason for that is that the interventions that appear in the model are handled differently for each group. So testing only in that time only applied to people who had symptoms. So if you had symptoms, if you were in the infectious group, then you might have gotten tested, in which case you might have gone into isolation. Whereas if you weren't tested, but you did have COVID, then you might have had worn a mask or limited your contact with people. And so each of those features is built into the model. And so instead of having to change the basic reproduction number over time, what you have to do is just pick the values of 3 specific parameters, and then you observe how the basic reproduction number changes over time.
Yeah, we did use a moving window to try to identify the reproduction number and how it changes over time. Still, it was quite difficult to predict accurately beyond 3 weeks, which were they
well,
were.
You were trying to do it empirically from data, whereas if you do it mechanistically, then you can still use data, but then you don't need as many parameters in your model. The more parameters you have in your model, the less predictive value it has.
Yeah.
So that's another reason why you couldn't go beyond 3 weeks, because your model had a huge number of parameters. And I mean, you may not have written them in the model, but
no, we didn't have. We actually I think only the reproduction number was a parameter. The other parameters that have to do with the incubation period and recovery times, those are well published, and we just took those off the literature.
Yeah, I misspoke. What I meant was that if you had done a mechanistic model for the basic reproduction number, that would have had a lot of parameters in it.
Yeah. And another challenge we had was we used the reported case counts to kind of fit our model, but the other challenge there was that not all COVID cases are reported, so we had a parameter in there that was a scaling factor, and there was a lot of confidence interval work.
So again, if you look at my COVID model that's that for March 2020 that's in my book, I put some effort into how to pick the parameters for the model, including parameters that are really hard to know, like what fraction of infectious people are pre-hospitalized. It's really hard to know that because some infectious people have symptoms, but they don't get tested. So they're in class I1, but you don't know which of the two, whether they're in I1 or still susceptible. So it's very difficult to identify the class for an individual. And so you have to use what little data you have that's fairly reliable, and then back out what the model parameters must have been. Anyone else? Edom, you have your hand up.
Thank you for the presentation. I wanted to know if there is a program to train modelers or mathematicians to be able to communicate their finding, their results to non-technical people, because
that's a really
during
good
the
question.
COVID, we had a story that about these people are going to die, and everyone was panicked. Like we're like, is human race coming to an end? Are we all coming to die? But because they couldn't communicate their results well, I don't think journalists have knowledge in mathematical modeling or whatever. So whatever they hear, they'll just jump on it.
I once did a research program with very talented pre-freshmen. So they just graduated from high school. They had really high SAT scores, really good at math, good grades. And the first year that we did it, we had them do a research project and they were completely unable to write a good report of their research project. I'm sure that all of those students could write a good history paper. So the next summer, we hired a graduate student from our English department whose specialty was teaching technical writing. And that year and every year after, we got really good reports from the students. My colleague who organized that program with me, and I wrote a paper on that along with the English graduate student. So shoot me an email and I'll point you to where to find that paper. It won't tell you everything you want to know, but it'll give you at least a few pointers. Let's see, somebody asked, quantify the low predictive value of accounting for certain factors. I don't know about that in specific cases, but another thing that I will point you to is that most of us have heard of Occam's razor, which says that that don't make things more complicated than they absolutely need to be. There is a statistical implementation that's equivalent to an implementation of Occam's razor called the Aka-Ika information criterion. If you haven't heard of that, try to find out about it. It doesn't appear in statistics books yet, and I don't know why. It was discovered in 1974, so we've had a lot of time to get it into statistics books, but it isn't yet. And essentially what it does is it assigns each model a score for how inaccurate it is, and another score for how complex it is, and it adds those two scores together. Lowest score wins. So if you have a model with a huge number of parameters, it might predict the data set that you have better than a model with only 3 parameters, but it won't win the AIC battle because its complexity is too high. That's another topic that's in my book that I didn't talk about today or even mention because it's empirical modeling, but I do have a chapter on empirical modeling and AIC is in there.
Yes, on that note, thank you so much for presenting and also answering all those questions.
Thank you.
Next